All right, let's go to the main part of today's class. It's called the recursion. Yes, so we can skip the recap. We have already done that. So in today's lecture, we need to actually we need to implement some programs that use recursion. So recursion is just calling functions of yourself, right? If you are a function A, you're calling A. You are function B, you're calling B. That's called the recursion. So you need to think recursively. That's the hard part. How to think recursively, because it's against our thinking process, right? Let's see a simple example. How to compute a factorial. Factorial means n factorial means n times n minus 1 times n minus 2 until 1. So here is what we typically write in a for loop, starting from 1, right? Each time from 1 to n, we multiply by this I. So this one will get the factorial. It's easy to understand, but we can also write it in a recursive way, right? What is n factorial? It equals n minus 1 factorial times n. Right? So it means we can write a recursion for it. Let's do it step by step. But if n equals to 0 or 1, then factorial is 1. Right? 0 factorial equals 1, 1 factorial equals 1. This is what we did inside this function. If n equals to 0 or n equals to 1, our output is 1. These are the very easy case. Right? It's called inductive, or in your high school in Chinese, it's called 归纳法, right? All right, so deal with the general case. As you can see, something interesting here, right? While you are writing this function, you haven't implemented factorial, but you will start using factorial. You have to assume factorial works for n minus 1 case, right? For assuming factorial works for n minus 1 case, we can get the result. Then how can we compute n factorial? It equals to the smaller one times our current n. And then we can return this result. But if you can understand this one, basically you know what is recursion. You are calling yourself factorial. While you are writing your code, you are calling yourself in it. This is what we meant by factorial, by recursion, right? This is the process we compute for factorial. We need to compute factorial of 4. Inside this function, we will call factorial again. Let's compute factorial of 3, right? In order to compute factorial of 3, we will call our function again, compute factorial of 2, and compute factorial of 1, because 1 is a simple case. It directly outputs 1, so it will return 1. After it returns, we go back to the outside and compute the smaller one. Smaller one is 1. 1 times our n. What is our n now? This n is this 1. We are computing factorial of 2, right? So in this case, n equals to 2. Then we can output factorial of 2 is 2. Then we will jump to the outside. 2 times 3. Then jump to the outside. Compute 4th factorial. So any questions on this?
This the other way?
No, it's not. It's more complex actually. Yeah, because each time you are invoke a function call, it's actually slower than the for loop one, but it's just an example of you can use recursion. You will see more complex examples, and that will be easier to solve using recursively. All right, so this one is a technique actually. We need to express a solution to a problem in terms of a solution to a problem of a smaller size, right? It's called a recursion. the way we can write it is like this. We can simplify the computation. We can write it down the equations like this. Factorial of n equals factorial of n minus 1 times n. This is our equation. And we need to deal with the special case, because if you only write this one, it will call forever, right? If you want to compute 4 factorial, you need to compute 3 factorial. In order to compute 3 factorial, you need to compute 1, 2, then 1, then 0, then -1, -2, -3, infinitely. So you need to tell it when to stop in your computations or recursions. And in this case, we use 0 or 1, but in many cases, that will be different. All right. Simple example, how to compute Fibonacci Fn, right? This is Fibonacci. If it's 0, it's 0. If it's 1, it's 1. For all the others, starting from 5, the result is the bit of 4 plus bit of 3. Similarly, if it's 9, it's 34. 34 equals 13 plus 21. Right? How can we write a recursion to solve that? Firstly, we can write down our equation, right? Fibonacci of n equals Fibonacci of n minus 1 plus Fibonacci of n minus 2. That's our recursion. Then what's the stop case, right? We can stop case like 0 and 1. If it's 0, if it's 1, we can stop. We don't need to call it recursively anymore. Let me see if we have a, no, we don't have any example. So let me show how to write it down. Let's try to compute Fibonacci of 5, right? It should be an integer or long, in case it's fine. So we need some input I. If you want to think recursively, it should be just one line, right? Return fib of I minus 1 plus fib of I minus 2. Right? Without considering the special case, this would be the simplest one. This is based on the recursion. So we can also have to deal with the special case if we have reached the I equals to 0 or I equals to 1. We could return 1. Is it 1 or 0? I don't know. Let's try it. Let me see. Oh, it's 0 and 1. So return I. Right. For the special case, I equal to 0 or I equal to 1, we can return I. Otherwise, we return I minus 1 and I minus 2 recursively called. Right. So let's see what will be the output. It's 5, right? And we can try another one. How about 9? It's 34, right? So it will be very easy to implement. And let me see. Yeah. So any questions on recursively thinking? What is recursively thinking? Before I writing Fibonacci I, right? I would assume Fibonacci I minus 1 is correct. And I would assume Fibonacci I minus 2 is correct. If these two are correct, if I'm adding them together, the answer should be correct. Right? It's called deductive. And when you are calling Fibonacci of 9, it's actually first calling Fibonacci of 8 and Fibonacci of 7. Right? While you are calling Fibonacci 8, it's calling Fibonacci 7 and Fibonacci 6, and so on. And it's actually very time consuming to do it. If you put, I don't know if I can tolerate 100. Let me try. If my machine will break, it takes forever to do it. Recursively, so recursion in here, because you are wasting your time, right? While you are computing 100, you are computing 99 and 98. While you are computing 99, you are computing 98 again, and 97. So it will take forever to finish. This is the recursive way. How can we write a for loop to solve it? How can we write a for loop? First one is simple, right? If let's say we need two numbers. One is called a previous. Another one is called previous of your previous, right? Wait, this one is 0, this one is 1, for example, right? In order to compute to I, it's actually easy. Let me see. For, let's call it n. The answer or not? Let me call it. Something like that. I haven't checked if it should be starting from 0 or n with n minus 1 or so. Yeah, it's hard to verify that. But if you are careful enough, you will know if this one is correct or not. But these are something you can do, right? If you have some variable to keep track of your previous one, and you have another variable to keep track of your previous one, then each time you can add them together, and in each round you can update what is the previous. They are sliding together, right? Sliding one after and so on. So let's see if this one works. I'm not sure because I haven't verified that. Let's use 9 or 8 as an example to verify it. Warning, no return. Oh. 21, is 21 correct? 21 is correct. All right, let's try 100. All right, 104. Oh, maybe it's too large. It should be a long type. Yeah. Anyway, I try something like long. Yeah, the answer should be long, right? Long. because it's a too large number. I don't know if long can work because it's such a large number. Yeah, I can make it double, but I don't want to do that. Yeah, it can work, right? Very large number. But anyway, it can finish it just in 1 second, right? Remember the recursive one, it takes forever. It takes forever to finish if you use the recursive one. So whenever possible, use a for loop. But if for loop is too hard to think about it, you could use a recursive calls. And the main problem in this recursive call is calling it again and again. Sometimes people use an arrays to keep track of the data, but it's beyond the discussion of today's class. Maybe in the algorithm class, you will know something called dynamic programming. You will learn how to store them so that you don't need to call them over and over again. But you're still using recursion, but you don't need to call them over and over again. All right, so that's the Fibonacci, right? I have shown you how to write a simple loop to compute it. And we can also talk about the efficiency whenever possible, use for loop. This is how we can think recursively, right? Using this example. And for example, if we want to test if a sentence is a palindrome is it equals itself when you reverse it. So like APA, right? When you read from the back to the front, it's still APA. It's called a palindrome. And here's an example, those are, right? R and R are equal, O and O are equal, and P, right? And let me see, is this one a palindrome? Yeah. A plane, panel, A and A are equal, M and N are equal, A and A are equal. You can check that. When you read from this side or this side, they are exactly the same, right? And similar to this one, go and GOH, right? When you read it, it's still palindrome. This is the problem you need to think, right? How can you do that? It's also very easy to use a for loop to test, right? You can use 2 pointers, one pointer to the beginning, one pointer to the final, and you can compare one by one. When there's some mismatch, it's not a palindrome. So our goal is, okay, if I give you the string S and return a Boolean saying is a palindrome or not. So this will be a question. So as a, yeah, any confusions about what is a palindrome? No, is it clear, right? You read from beginning to end, and then reading from the end to beginning. They're exactly the same. A, M, A, N, A, P, A, M, A, N, A, P, right? You're reading backward or forward, it is the same. So your goal is to implement this kind of function. So how can we do that? Think recursively. Step 1, you need to think, how can we verify, how can we simplify this input, right? Several possibilities. Easiest one is remove the first one, remove the last one, or remove both the first and the last, or remove a character in the middle, right? There are many different ways you can think about it. Or you can cut it into half, right? Many different ways. Step 2, how can you combine the solutions with simpler of this one, right? Don't worry about how these solutions are solved. You could assume this function works for a string that's a smaller size. If we want to test ROTOR, we can assume someone already implemented that function, tells you, OTO, is it a paradigm or not? The function is already correctly implemented. You can think about it that way, right? If that is the case, then we only need to compare the first and the last, right? We compare first and last. If they don't match, it's not a paragon. If they match, we continue with something in the middle. It's recursively thinking. And then we can find the solutions to the simplest input. What is the simplest input? Empty strings, right? Sometimes when we talk about any questions, sometimes we simplest 0, 1, empty strings, shapes with no areas, and so on. So any questions like that, you can first solve the simplest one. And you want to investigate a slightly larger ones, right? If it's empty string, how about just one string or one character? How about 2 characters, right? If we go more and more, you don't need, because after 3, you can reduce it back to just the 1 character problems. So these are the one thing to note is the infinite recursion, right? A common error is you didn't specify the simplest input correctly, so that it will call your function recursively infinitely. It will never end because you didn't specify the endpoints for that. Right, so let's write the simplest one, string with 2 characters, or a string with a single one, or a string with an empty one, right? After that is done, then we don't need a string with 2 characters, right? We can remove the first and the last, and it will become an empty string, right? So this one or this one, choose one. Most likely we will choose the empty string. Empty string is always palindrome. Then we don't need the 2 characters one. So in our function, first line it would be if the string contains string length is 1, then it's a palindrome. Second line would be if the string is empty, return true, right? So the simple case would be easy to write. And then implement this one, combining the simplest case and the reduction, right? After these 2 lines, we say if the first one matches the last one. If they match, it's not a palindrome. If it match, we return the output of the middle. So let me see if we have one. Yeah. Special case, if S the length is a string, right? String's length, if it's less than 1, either empty or a single character, it means it is a palindrome. It's the simplest case. Right, then how about the other ones, right? We have the first one as 0, the last one as n-1. We compare these two, right? If the first character and the last character doesn't match, we go to the else, return false, which means it's not a palindrome. If they match, we construct the shorter version of the string, starting with 1 and ending with the n-2. So this function you will learn later is just removing the first and removing the last. Construct a new string that contains the middle, and then you can return this one, right? Return the palindrome of this shorter version. So this is about thinking recursively. Your output should depend on the output of your shorter version. Whenever they meet a mismatch, they will return false and jump out, then jump out, then jump out. Any questions? Focus more on the thinking process, right? It's just a function calls, right? It's nothing but a function call. All right.
It fails. If it fails and then the middle of the character with the it's on the stack.
Yeah. So for example, if you are return false, right?
Yeah.
Jump to the caller, someone calls your function, you are the shorter version of someone else. You will return false. Then you will jump out to another function. then return false, then return false, then return false, return many more times. Any questions? All right. How can we do a permutation? How can you think recursively? You don't need to write down the code. How can you think recursively? If I give you a factor of numbers, right? 1, 2, 4, you need to list out all the possible permutations. 1, 2, 4, 1, 4, 2, 2, 1, 4, 2, 4, 1, 4, 1, 2, 4, 2, 1. How can you do that? What are the simpler questions compared to this? In our previous one, right? The simpler question is, if we want to solve for string S, you need to solve for a shorter version of S, right? How about this one? If you need to output a permutation of 3 elements, what are the simpler problems?
First number can be one equal for I equals 0, I more than 3. So I print first number. And then in this loop, I print the other 2.
Yes, correct. So the simpler question is permutation of 2 numbers, right? If I give you permutation of 2 numbers, you just append 1, right? Or by the way, permutation of 2 numbers, you push back a new one. Permutation of 2 numbers, push back a new one, right? And whenever it give you a output, let me see. Yeah. So how to solve permutation of 2 numbers? You solve the permutation of 1 numbers, right? If you have permutation of 1 numbers, you append 1. So that will be similar to the previous one. Let me see if I have solutions. Nope. Okay. So the questions are actually easy, right? If a vector has n numbers, what are the total number of permutations? N factorial, right? And what are the input-output type? What is the input type? A vector. Right? What is the output? Vector or vector. Right? You have a bunch of vectors. Yeah, the hard questions I will skip that. You can figure out by yourself. But let's do the simple one. Recursions. Let me delete. Right. This is what we want. We want what is our input? Our input is a vector. Our output is a vector of a vector. Right. So let's see. We can have a for loop. So the first question is, how can you get the ith element, right? Assuming ith element is x equals v of I. You have get the ith element. And then next you need to delete, actually, delete x from V, right? Get a vector V prime. If I can get a V prime, that's delete x from V. It's a new vector, but with a smaller size. Right? It's a smaller size. And next, what we need to do is we can call permutate on V prime, right? It will give you the permutation of smaller size. If your input is have 3 elements, you can get the permutation for 2 elements. Let me walk you through an example. For example, initially I equal to 0, right? You can get the x of I, which x is 1. Then you can delete 1 from the V. Then what you will get is vector V prime is a factor of 2 and 4, right? So this is the V prime if for I equal to 0. And you would ask permutation of V prime to return something to you, which is, let's skip this implementation first, right? It should give you something like 2, 4 and 4, 2. It's a 2-dimensional vector. Permutation of 2 numbers, it should give you something like this. If you assume this permutation is correct, right? So permutation of V prime should give you 2, 4 and 4, 2. So how can you construct a new permutation? We could have 2, 4, 1. We create 2 more. One is called 2, 4, 1. One is called 4, 2, 1. Right? We want to construct this one, these 2. And when you look to next round, I equals to 1, so x becomes 2, and you will get a permutation of 1 and 4. Then it will have 1, 4, 2, 4, 1, 2, right? Then next round, when you access the last element, it will give you the permutation of 1 and 2, right? So let me write it down. Maybe easier to understand. When I equal to 0, x equals to 1, this is V prime. Let me. When I equals to 1, right, x becomes 2, and we can delete the 2 from V, and we can get 1, 4. And the permutation of 2 numbers will give you 1, 4 and 4, 1. For 1, it becomes 1, 4, 2 and 4, 1, 2, right? And in next round, when I equals to 2, x equals to 4, and V prime becomes 1 and 2. Permutation is 1, 2 and 2, 1. And you can push back to it, which is 1, 2, 4, and 2, 1, 4. Right? This is how it works. Your thinking process. If someone give you the output of permutation of smaller numbers, right? 2 numbers, if it's working correctly, you can just push back the last element. Similarly, here, if your count number is 2 and other people give you 1, 4, and 4, 1, then you can push back the 2, and then similarly here, right? This is our thinking process, not the real code. So any questions? Yes.
Wonder if you propose that it's out the vector that more than 3 numbers.
Yeah, you can work for more than 3 numbers, right? We are iterating through all the V size. All the elements of V. If the vector V size is 4, right, we'll iterate all the 4 elements. Each time we take one out. Each time we take one out, for the remaining 3, we get the permutation, then adding the last one back. Right. It is exactly the same as the if you mathematically compute how many permutations are there if you have a n numbers, right? It's n factorial. So you have n minus 1, you output something, you need to copy your data to each of them, right? So it can work for more than 3 elements. You can try it out. Any questions? This should be a hard one, right? It's really hard. You need to think more carefully about how it can work. So your basic thinking process is like this. If you can solve for smaller questions, how can you construct from the smaller solutions to a bigger solutions, right? This process is not that easy, but this is one you can think about it recursively. All right, so let me write down how to implement it. Assuming this is your answer, right? And at the end, you can return the answer. Right? So this is the one. And assuming you can delete to V prime, we call it vector of integer, right? It's another V, that's called V2 equals V dot, I don't remember the name, maybe delete, maybe something. Let me test it, check it later. The index of I, right? Is it delete?
Erase.
Erase, okay, erase. Erase item, and assuming you have a new one, have your smaller result. Vector of integer. Right, assuming you have the smaller answer, and you can do a for loop for int k equals to 0, k less than smaller dollar size plus k. For each of the smaller solutions that the with the smaller size is created, we need to access one of them, each one of them, right? When we access the first one, we push back our x. When we access the next one, we push back this x. This is what we do. Right? This is exactly what we did in here. If we have the permutation of the smaller size questions, we have 2, 4, 4, 2. Then when k equals to 0, smaller k is 2, 4. Right? In 2, 4, we push back x equals to 1 now. So it becomes 2, 4, 1. We push this smaller k back to our answer. This is our first answer. Our second answer will be for 2, right? Push back X and then come back to the answer. So this will be exactly the same as this one. When we access the answer of the smaller questions, then push back our X, the deleted one, back to the answers. So yeah, that's almost done for the recursion. We haven't to deal with the special case. But any questions? So when you are writing recursions, the thinking process is really important. How to split this problem into smaller ones, and also how to construct it back to the original solutions. So let's deal with the special case. Special case is actually easy. Let's call it size. Right. If the initial is empty, we return empty. Initial input vector v is empty, we return empty. If it's not empty, we solve it for a smaller version, then get it back. Yeah, question.
Just wonder if there are numbers, similar numbers.
Oh, it's also, yeah, we don't care about that. That will be more complex ones. Yes. Any questions? This one is more focus on the recursions, right? Focus on this thinking process. Special case and recursion. Let's try it out. I don't know if it can work. Oh, I'm implementing the fib. A lot of problems, right?
Maybe
Erase I.
erase.
Yes.
I.
Yes. Let me see. It's a constant. Yeah. Wait a minute. Let me copy it once. Yeah, forget about this one. Don't pay too much attention on it. There's something that you haven't learned. Wait, I didn't print? Yeah, I didn't print. Couldn't be that way. Sorry. Wait, is it empty? Oh, maybe yes. Let me check out this erase function. it should work. Yeah. It's really tedious. Wait to that again. Yeah, it takes time to debug. Let me see. All right. Anyway, you guys can try it out because we don't have time for a full version. It's actually a hard question for you. All right. If you don't know how to do it, it's fine. The more important part is the thinking process. All right. If you need a solution for 3 elements, think about solutions for 2 elements, and then add 1. Right. This thinking process is very important. And typically, we can have something called recursive helper functions, because these functions are something that's slightly different from the original one, as you will see it later. So in our palindrome example, it's efficient to construct new ones, but rather than creating new ones, right? These functions can skip over matching the letters pairs by adjusting the starting point and the end point. We don't want to create new strings like in the old palindrome. So how can we do that? Let me see if we have one. Yeah. So this is the original palindrome functions, right? And we have our strings. We can have a helper function here. In our old palindrome functions, we will create a new string every time. That's tedious. So what we want to do is we want to implement a new function that's from a start to the end. Just to check everything in the middle, are they palindrome or not? So for the main or for the real functions, we will test from start to end. Are this string palindrome? But in the middle, we can change. We don't need to construct a new one. You can say compare s of start with s of end, right? If they match, we can test start +1 and end -1. Is it clear? Let me see if I have the example. No. So let me see. Yeah, maybe it's better to write it down somewhere. All right, let me close it. Right, this is our functions. And in the original one, we will create a new string in each palindrome each time. But now we will change it here. Right? Here we say, how can we call recursively? If s of start equals s of end, what we will do. And for what if it doesn't match, right? We can return false. What if they match? Yeah, we can call this one, right? Return this one of s start +1. Okay. +1 until end -1. Right? So we don't need to create a new string each time. We're using constant reference, so the string is not copied, it's efficient. The only thing we change is the index, right? From start +1 and -8 and -1. So in our helper functions, we might say something like that. We say it is a function to check, see, if S of start to end is palindrome, right? If you believe this function can work for start +1 to n minus 1, then you can use this one to construct a bigger problem, right? When the string size is larger, if it can work for a smaller version, you know it can work for larger version. Right? This is thinking recursively. You're calling yourself over and over again. The reason we don't use this function as our main function, right, compared to is palindrome, is because this one is more user-friendly, right? User only need to give you these strings. They don't need to know how you are implemented using something like the index or positions. You don't need, the users can directly call is palindrome hello, right? They don't need to put 0 or length -1 here. But this one can call that one to skip this creating of new strings. Let me show you the old one. The old one, where's the old one? Wait, took so long. Yeah. So this is the old one, right? Old version. The problem is in here. Each time we are creating a new string, and then test if this one is a palindrome or not. But in here, we don't need to create a new string, right? We are just change the starting point and end point. Any questions? So how can we write the special case? What is this special case? Some special case return true. What are the special case? If start meets end, right? If there's only one character, it is a palindrome. So we could say if start is less than or equal to end, it means we are checking a single character for an empty character. Let me give you an example, right? If we want to check ROTOR with start equals to 0, end equals to 0, 1, 2, 3, 4, right? We want to check this one. We would call ROTOR with 1 and 3, right? Then we will call ROTOR 2 and 2, right? So what does it mean by 0, 4? We are checking if ROTOR is a palindrome, right? We're checking ROTOR is a palindrome or not. So what does it mean by 1 and 3? It means we are checking OTO, right? 2 and 2 means we are checking is 2 a palindrome. And for the last special case, when the index match, we will directly return true, right? If they doesn't match, we will compare the start position, rotor 0, which is R, with rotor 4, which is R, right? So because they match, we will call this function, which is the second one, rotor 1 and 3. Right? Actually, we are checking is the positions from O to O are the parallel. Yeah, question.
I wonder one of the first if is not start with equals to n.
Pointer or oh yes, you're right. Yes, I read it wrong. Sorry. Yeah. The special case is greater than or equal to n. Yes. Any more questions? So there will be 3 times, right? Is this function will be called. First one with 0, 4, second one with 1, 3, next one with the 2 and the 2. So it is a recursion. All right, let me jump back. Yeah, before I jump to here, are there any questions why we need a helper function? Are there any questions on it? It's clear why we need a helper functions, right? When you are designing your recursions, in many cases, you will need a helper functions because the way people call their functions, they want the parameters to be simple. But in your recursions, sometimes you need something like the indexes. Which positions, which is the starting position, which is the end position you want to compare, so that you can skip the copy of the new string. Right, we have something else, which I call mutual recursion. It's actually a bunch of functions. They are calling each other, right? Function A can call function B can call function A, and recursively. It's not actually a recursion, you can think of that way. It's just a bunch of the function calls. So as you can see, if we define an expression, right, expression like this, 1 minus parenthesis, 2 minus parenthesis, 3 minus parenthesis, 4 minus 5. How can we evaluate this one? We can think from the highest level, what is an expression, right? It's just some term plus or minus some term. And what is a term? Term is also factor multiply and divide by some term, some factors. And what is a factor? Factor could be a parenthesis plus some expressions and or just some numbers, right? So as you can see here, expressions. When we meet these expressions, we need to call it here again. Expressions need to call the term function need to call the factor function need to call expression function, and we come back again, right? Over and over again. The end point is the number, right? When the factor is a number, we stop. So here is the function call. And as you can see, this way also meets the parenthesis or precedence of the multiply and the plus, right? If you have an expression, for example, if it's 3 plus 4 times 5, it needs to compute 4 times 5 first, then do plus 3. Based on our the graph, expressions contains term plus term, right? It contains term plus term. So in term, it contains factor multiplied by factor. So by this tree, we know 4 times 5 will be computed first. It will construct a term. 3 will become a term. Then it will becomes an expression. So this one, respect to that, multiply has higher priority than plus, right? And in here, if we put a parenthesis, we say expression is a term, right? The term contains factor times a factor. Because expression here cannot break this parenthesis. So it has to respect this one is a factor. And then, as you can see, 3 plus 4 will be computed first, then a and multiply. So this one is an example of how we build and call it grammar tree or abstract syntax trees. But you don't need to know the name, but here is just some examples, right? And as long as you write functions in this way, you can compute the correct output. So we can have 3 functions. First one is the expression, second one is the terms, last one is the factor, right? And they will call each other the expression term and calls the term value, right? Expression value calls the term value to check if the next input is plus or minus. And the term will call factor value. And we will check if it's a multiply or divide. And a factor will check if it contains a parenthesis or not, or a digit. And the termination of this regression is caused by the numbers in your vectors. All right, so here is what it looks like. Right, in our expressions, we can first call a term. But expressions contains term plus minus term. So we start on term. Then we look at the next one, is it a plus or minus? Then we can get the plus or minus, and if it's then we can evaluate the remaining ones. If it's a plus, we plus. If a minus, we minus. Then return a result. So in an expression values, this one is very easy to write, right? We deal with the first term, deal with the opcode plus or minus, then we deal with the remaining term, then we are done. In the term, right, the terms are constructed by factors multiply or divide by factor. So we compute the factor, look at if the next one is multiply or divide, then we evaluate the next factor. If it's a multiply, if it's divide, then we output, right? Similarly, in the factor contains either parentheses of an expression or just some numbers. If it's just numbers, it's the end of a function call, right? We're done. If it's a parenthesis, we need to call expression again. We know there's an expression inside your function calls. So this one is 3 functions, right? Calling each other, and until this one will end these recursions. The special case is in here, and all the others are recursions. When you get back, you can read this code carefully. Any questions? Okay, so peek is looking at the next character, but without reading it, without consuming it. It's a producer and a consumer. Seeing peek, look at the next character, right, but don't read it. And then you can get or read it. This one is the same as read, but you don't store it anywhere. You can check for more when we talk about the streams class. There's a peek, there's a get. Yeah. But focus on the function calls. Recursive is just about function calls. A single function can call itself, or multiple functions can call each other, and recursively. Pay more attention to the thinking process. When we talk about the efficiency, we said recursions are slow, right? Especially when we talk about the Fibonacci sequence. We have Fn equals Fn minus 1 plus Fn minus 2. And in your program, maybe you can try something between 30 and 50, right? You can try how many times this function is called. And what are the numbers when they get into this function? Let me try this. Let me see if yeah, this is the output. When you are trying to compute Fibonacci of 6, it starts compute Fibonacci of 5 and 4. In order to compute 4, you compute 3 and 2. In 2, you return 1. In 1, you return 1. And in order to compute Fibonacci of, yeah, this is the return value of 3, because you have already finished 1 and 2. So you can finish the output of 3, right? And then you are entering Fibonacci of 2 again. Because of the 4, right? You are computing Fibonacci of 4, you need to compute Fibonacci of 3 and Fibonacci of 2, right? So you will see the calling process. And as you can see, many times, let's see how many times n equals to 2, n equals to 2, computed once, n equal to 2, computed twice, n equal to 2, computed 3 times. It's computed over and over again. Because when you are trying to get a 6, you need to 5 and 4. You want to get a 5, you need a 4 and a 3. You want to get a 4, you need to a 3 and a 2, and so on. So as you can see, 4 is 4 called twice or once? Once. Yeah, there are some dots. You can find out. It should be called twice, right? So this is the efficiency of that one, that Fibonacci, because it calls itself twice. This one, it calls itself twice. Fn equals Fn minus 1 plus Fn minus 2. So it's very slow, as you can see. This is how we can call it, right? In order to compute Fibonacci of 6, you compute 5 plus 4. When you are computing Fibonacci 5, you are actually computing Fibonacci 4, right? But here you also need to compute Fibonacci 4. So, and if you look at the 2, once, twice, 3 times, 4 times, 5 times. Each one is a function call. So in order to compute 6, you have a lot of function calls. And it grows exponentially. So it's a slow one. This is by the way, right, we use the example of previous and previous one to show you the examples using a simple for loop, right? So any questions on it? I want to stop our class in here. Any questions on the slowness of Fibonacci, or any questions on everything we have discussed today? So all right, so you need to when you get back, you need to spend more time playing with the code and trying to figure out the recursions. So especially for the recursions, when you are in the future, in next class, we will have some something about the wait. Do we have Hanoi Tower? Yeah, this one. Right. This one, if you can think it recursively, it's very easy to solve using recursively. So if you have already understand everything we have discussed today, you will be able to solve this question. All right. Go back and think about it. We will discuss it in next lecture. Bye.
它在这里，它处理的是同时处理，还是它先处理完上级的再处理下级？
一般人处理完一个，他会沿着这个一直下去，然后照这个在这个下去，再上来，再上去，再
哦，这样就是，那这个 helper， 那个 helper， 那个我不太懂，它为什么要多加一个 helper， 就是为了
是别人要用这个函数的时候，别人 就你回到那个 palindrome 那个方法，就是别人调用函数的时候，别人只想这样子调用，但这样子调用你要调用自己的话，就要形成一个新的 string，形成一个新的 string 的话比较花时间，就你不如只记录一个 index。但别人不想调用你的函数用这样子来调用，别人还要给你一个参数 start，给你一个参数 end，别人不想这样，别人只想要有一个这样子。
然后我在这个 helper 里面去获得它的 index。
对对对，是的，是的。
那怎么样把这里的参数传到就是另外自己的或者
对，这个就会一个一个拷贝过去。
哦，return 这其实就是返回多个值的一种方法。
返回一个值就是 return， 这个就是这个不论返回什么，它就直接 return 出来就行。
什么意思？
就比如说这个函数 return false， 那么你就直接 return 它的结论，它是 false 你就 return false， 它是 true 你就 return true。
就相当于是他用它的索引在这里已经读取到了那个 start 和 end， 然后就直接在这里面调用这个函数，就相当于把参数传过去，
对，
return 就在这里。
对，是的。
我把它那个写完了，那个必须要加那个基准条件。
哪个？
就是中心排序的那个。它必须要加一个基准条件，不然的话，
一定要是1或者2的时候加入基准条件是吧 ？OK，
不然的话它跑不了。基本上运行的话也是，就是多个数也是可以的。
对，都是可以的，就不涉及数量的问题，你5、6、7、8都是可以的。
还有这个轨递归是什么？轨递归就是我们费波那契用的就是那种一个条，
对，就是
轨递归，我就不太看得懂它这个。
轨递归的意思就是说它会编译器会自动把你转化成非递归的事情。就你是用递归实现的，但如果你是最后一句话的话，递归的函数会把你转换成不是递归。它这个比较难考虑，就是这里哈，它这里会你每一次函数调用，它会生成一个站和一个堆。
对，
它每次站堆站堆，但这个它不会形成站堆，因为它知道它是最后一个返回值，它直接用它的值就可以，它不需要生成一个新的站堆。这个是编译器会做的一些优化，这叫伪递归。
这地方是不是写错了？就是这个函数。
对，是的，应该就是这个名字，是的，我这里写错了，是的。
老师能不能看看你那个就是那个就置换那个就是那个代码？
置换是这个吗？还是哪个？
这不是那个，是那个124的那个。
permutate。
对。
是在哪个里面？写在 fib 里吗？这个吗？
对，想问一下这个，后边这个循环，就是这个循环，
这个 K 的循环是吧？
这个 K 的循环是吗？就是比如说哈，第一轮 i 等于0，那么这个 x 就等于1，那么这个 v2 就等于24，然后这个 smaller 就会等于24跟42，然后这个 K 循环的时候 ，K 等于0的时候，你得到的 smaller K 就是这个24，第一轮 K 等于0的时候是24，K 等于1的时候就等于42，那么你得到24的时候，你 push 这个1进去就得到241，第二轮42的时候 push 一个1进去就得到421。
懂了。
这里唯一的问题就是我忘了把这个给初始化，其实应该给它一个初始化的东西。
这种方法要试试，
这样子就可以了。这个函数应该就可以运行了，无所谓。这个output或者是1的时候，这个等于1的时候，比如说，等一下啊，要让它运行的话，就是这里不应该从0开始，应该从1开始。从1开始的话就是对的。从1开始的话 ，answer 直接 push back 那个 b 就可以了。对，这样就是可以运行了。我上课没有时间调，就这样子，就是 OK 的。对，你从一个 element 开始，一个一个增加，一个增加，一个增加。对，这就是递归的。
季老师。
我也来一个。
你说。
我说我也拍一个。
你也拍一个。OK，
我也写了一个可以实现
写了好久，但是我至今都没法解释它为什么跑得起来。
能跑就行。
我感觉递归这种东西，很多时候你没法，你很难把它那一整个链条给
就是你在写这个时候，你思路一定要清晰。你什么时候思路，比如说混了，然后你就发现你写错了，
就是因为像我写的那个，它是同时含有 for 又有递归，所以我想了半天都没有想到它的那个 执行顺序到底是怎么样的，太复杂了。
老师，这个我不太明白。
啊，就是这里，对，你说，
就是它这里定义了这个 k，然后呢，它为什么
就是第一步 smaller 等于什么？i 等于0的时候，smaller 就是这个，
对，
嗯，然后这个你 k 等于0的时候，smaller 0就是24，
你问一下这个是什么？
哪个？
因为这里的
因为是
它
去掉，
索引为 i 的给删掉，
对，就是这个
把 v2中索引为 i 的那个元素删掉。
对，
啊，
就是你 i 等于0的时候，i 等于0 x 等于1嘛，对吧？这里我要把 x 从 v 里面删掉，就一开始进来是124嘛，我要得到一个24，这就用这个 erase 这个函数，把第 i 个删掉。当然这个涉及到那个叫什么？这个叫什么 iterator 你们后面会学到。就大概你们去读一下那个官方的文档就知道大概是这么写的。对，这就是删掉一个东西。他就把第0个删掉，就得到24。得到24以后，你在递归的调用，它就会告诉你一个结果。你假设它是正确的啊，当然你不知道它得出的结果是
为什么他会就
嗯
就得到24之后又可以得到42啊？
这个是我的假设。
你的
我的假设是更小的问题，它永远给我正确的答案。
嗯，
那我就先把正确答案写在这里，对吧？然后如果对假设它是正确的，recursion 就是这样，你假设它是正确的，然后再做一个更大的问题怎么去做，对不对？它的 job 也是一样，你假设对于更小的字符串是正确的，那么比如说增加2个字符串，你该怎么去做？就这样一个问题。
到时候报错的话就很难报。
对，报错 recursion 的调试有点难，对的。真的。但是只要你的思路过程是对的，基本上就 OK。就你假设它是正确的以后，比如说怎么样形成一个更大的一个结果，这个就是比较，这个比较
那这个要怎么实现啊？
那个
24
24跟42，我可以告诉你，permutate 已经实现了，你不用管它怎么实现。假设已经实现 ，recursion 就是这样。对，
真的想不明白。
就是你在写 permutation 的时候，你还没写完，你就假设它已经对于更小的情况已经能够执行了，并且是正确的，就跟那个什么，那个叫什么来着？就跟，哎，这个 match 在哪里？就以这个为例哈，就以这个为例，就你的思考过程是这个样子的。比如说，你要实现对于它的判断，你的假设是对于5个字符，我不知道它对不对，但是对于3个字符，我假设这个函数已经 OK 了，绝对是正确的。那么我怎样去让它去完成5个字符的事情？这个就是一个递归的一个意义。同样对于这里，我假设它对于2个量，它肯定是对的，肯定是对的，我就不需要管它是怎么实现的，我就告诉你 OK，它会 output 这个东西，output 了这个东西以后，你去怎么形成一个对于3个变量的一个处理。
哪里可以看出来它是这一步可以实现的？
你看不出来，你只能假设它是这样。
你可以解释一下这个算法吗？
老师，你能从头
等会儿啊，你说。
就是从头开始，就是
OK，从头开始啊。
对，
我进来一个 factor，还有3个变量，1、2、4。
对。
这里肯定会跳过嘛，size 是3，对吧？
对。
然后我进到这里，i 从0到3，第一步 i 等于0，i 等于0，然后 x 就得到它的第一个变量是1，对不对？然后我想要形成一个新的 factor，它只含有2个变量是2、4，我就用这个 erase function 得到一个2、4。然后你的思考过程是 ，OK， 我假设 permutate 对于更小的 factor 是可以用的，是100%正确的，那么我就不需要管它是怎么实现的，我就给你一个答案，它的结果就是2442。比如说就是这个 smaller 就是这个2442。然后我再对它每一个进行便利，可以从0一直到1，对吧？smaller 0就是这个24。然后有了这个24以后，我只要把1给它 push 进去，它就是一个新的一个 permutation，对不对？同样的，如果对于比如说他给了我一个42，我也把1给 push 进去，它就得到了一个421。这个就是一个从一个小的变成一个新的第二轮 i 等于1，我把2从 factor 里面去掉，就得到了14。我假设 permutate 可以对2个变量执行，那么14是正确的，它就会给我14和41。同样道理，我把2 push 到后面，那就得到142和421。然后后面也同样道理，这样最终我就得到6个，1、2、3、4、5、6，对不对？把它们合在一起， 就是我的结果。
我们14和414哪一步就
在上
交换
面不是不是 permutate
哪个？
就
在这里定义的吗？
就为什么它可以24交换？
24哦，我是假设这个 permutate 是可以用的，这是一个
是给它定
就是
的那个是怎么实现24和3
这么实现24，对不对？OK，
那就重新再来一
对，
遍。
实现24的时候，它在 call 了这个 permutate 24这个函数，对不对
嗯
？permutate 24这个函数我进来 v 等于24，
嗯
24的时候它的 size 不等于1，我进这个，
把第一个删了，然后
对
添加到后面。
对
哦，
然后我就要得到一个 permutate of 一个 element 的一个 factor，对不对？
那就
然后就是第一个
对，就是这个，
那就第一个它就一直满足了。
对，
你知道这里然后满足，然后那个
我这里再写下来，好，在调用这个的时候，我是怎么得到24跟42的呢？我再靠那个方程，对吧？靠那个方程，它的 v 就等于24，然后同样道理 ，i 等于0，x 等于2，
24、23，
哦对，24，然后我可以把它从那个里面 delete 掉，对吧？这样的话，我的 v prime
是
比2哈，就等于一个4。
嗯
我假设你可以给我一个 smaller 的结果，或者我叫它 permutate 哈，permutate of v2，会得到一个什么呢？会得到一个4，对不对？哦，可能是我这里写错了，对，我这样的话就永远只能得到一个数嘛，不对，待会儿吧。然后我的 output 就是4逗号2，对不对？这是第一轮。
对。
然后第二轮 i 等于1的时候 ，x 等于4，对吧？然后我的 permutate of v2呢，会给我一个2，然后我就会 output 一个2，一个4，然后我会把两个组合起来，就会得出这样一个24跟42。对，它会不停的调用自己，但是在你在思考的时候，你不要去思考这个24是怎么实现的。如果你这样想，就想复杂了。对，你就假设它就给你真的结果了，你该怎么去处理？
那我就假设说，然后实验的时候失败了呢，
失败了你就要去进行调试了。
要讲这前面的过程。
失败了你就真的要进入每一步的过程去看。
就是你假设的那一步，就是具体体现在。
假设是这步，我假设这个 output 直接给我2442了，你后面该怎么办？对，但我其实没有仔细的进去看它到底会不会生成这个，因为我代码还没写完呢，对不对？我写到这儿的时候代码还没完全没写完，我只是在告诉你 OK， 我可以得到一个更小版本的正确答案。
那我
所以这个代码能实现2442这道数吗？
可以的。
对，我们
已经可以实现了，对的。
居然不懂。我们是这样，我们其实知道，就是你想要假设这个，但是我们不知道怎么用代码体现出来。
就不知道最底层的那个2442。
对，就是说，例如说我们想那个写 painting，就是我们知道要怎么做，往左往右那样子，但是我们不知道怎么用代码把它给表示出来。
但是你们不用 for loop，你们可以一个一个写，会写，对不对？然后你们把那个转换成 for loop 会写，也会写，对不对？其实你们思考的时候，其实你们把所有事情都混在一起想，就会比较复杂。就像我讲的那个一样，你把它一个一个分解开，比如说就叫 paint to write， 告诉你它起始地址，告诉你颜色，你会不会写？这是一个很简单的写的，对不对？你肯定写起来非常容易。然后有了这样一个小函数以后，你会去想，这样一个大的函数该怎么写，对不对？然后一个比如说我要右边要去上面等等，该怎么写？这个时候你也是会写的，就是你最难的问题是怎么样把它一步一步分解开来，分解成更小的问题，更小的问题，更小的问题，每一个都是非常简单的去把它实现起来。就这样是一个你们需要训练的过程。
还有一个就是刚刚那个 size 的那个。
我想问一下我一个问题。
你问。
就是我之前写了一个程序，就是lab 课第2个程序那个我取交集和并集
然后很难 debug 发现这个东西，GPT 也检查不出有什么问题来。
我看也是什么，
这个很长。
还有没有我这？哇，你这确实猛啊！哇，这是200多。
也太长了吧？就是
就是如果拆分成很小一个模块，我就觉得 debug 非常难。
你要把它一个个拆开来，像我这个函数一样，像我这种函数一样，把它一个个小的给它拆开来，这种一个个小的，把它拆成一个个小的，每一个小的函数都 debug 一遍，都测试一遍。你有什么样的 input，什么样的 output，就给它测试一遍，然后再去测试大的。
太快了。
但是我发现小的没问题，一大起来就不行。
你把它每个都拆成小的，其实对你来说，比如说你一个函数运行测试完正确以后，你就不用管它了，你就假设这个函数是绝对正确的，你不要去调试这个函数，你就剩下的剩下的逻辑。
老师就是
他
不会报错，他就是会出现一些复数，然后或者是直接没有输出跳过去了。这是空间的问题。
这个很难讲是什么问题，可能你写的时候有些地方写错了。
你问问 GPT-4试试
啊？
我问的就是 GPT-4啊，然后
GPT-4你不如问 TA， 真的。
好，
有这么多 TA 的时间你们不去用，你就是进 TA 的时间。
GPT-4吗？
有啊，有 GPT-4。
哦，
对，
好像网上也有教程说可以白嫖，但是我还没搞。
什么？哦，所以那问完了后。老师，
我
们先问那个 size，就是就是我们
是那个 array 那个是吧？
对，array 那个，就是第二个他出8那个结果，就是他明明想要算的是整个数组的 array 的，整个 array 的。
是的。
对啊，但是他
因为这个函数它不知道它的 size 是多少。
但是我后面 int size
对，你给了10，对，还是不知道。
对啊
，compiler 不知道，他会 ignore 这个10，他会。
但是专门 int，
但是我
然后我输的是 a 逗号10。
你是说在这里写把 size 复制为10是不是？
对，
没有用的。它对于计算机来说，a 和 size 是2个变量，它们没有组合在一起，它们没有任何关系。这是你的想法，对，这个是你的想法，你觉得他们俩是一起的，但是同时你可以给 size 1也可以，负1也可以，10也可以，任何15值都可以。对，这个你电脑是不知道的。
那所以它到底调用的是个什么东西
？size of 吗？它只是看它第一个变量是什么样子。
就是数组的第一个变
量。对。
那你要怎么写？就是你定义的是
你想得到它的 size 吗
？A10的 size。
对。
你想得到 A10的 size， 你就给它一个 size，print size 就行了。
就是我们没有办法
没有办法
函数来。
对，是的。
好的。
这种情况下，它 size of 调用的是储存 A
的多少个
指针的大小吧？
这里函数里面是指针大小，
因为如果说你是要调用数组中某一个元素的大小的话，它应该是可以加一个 A 中括号什么的。
不一定，我想想看，到底是 A 还是 A0的？
就是你不知道具体。
就是我在 main 函数中想要算 size，我用的是 size of ARR 除以
有可能
size of
是
ARR
中括号
0。
对，有可能是指针的大小，没错。你可以把它改成 int 试一下。
我看的解释是，你自己定义的函数，如果输入只是一个指针的话，
对，
它会是一个数组的话，它会退化成指针。
对，它就变成一个指针了，没错。
对，
是的，你说的对。就是你给不给它10都无所谓，它就是一个指针啊。
所以我就在想，那我能不能在这个函数内部对这个退化了的数组进行解引用，
就可以这样子
把它变回一个
数组，基本不大可能，基本不可能，因为它已经忘记了它有多大了。
啊，
你只能得到某一个变量，比如说 A1、A2、A3可以，
但是它退化成指针嘛，那指针就是说指向这个数组所储存的那个地址。
对，
是这样。
那我解引用不就是调用那个地址内的那个数组吗？
但你的地址只是指向了第一个变量而已 ，A0而已。
那我会
对哦，
指定这个数组哪个元素再解引用。
这个可以，你可以用 A10、A2、A3都可以。
想问一下，就这里，就它传入参数这括号有个10嘛，是指就传入这个数组下标为10那个元素传进去吗？
不是，
那这个
写不写10都没有用的。
哦，
就是要写成这个样子，
就一点用都没有，
一点用都没有，
就完全一样。
对。哎，
然后那个
你上次说的是啥来着？我没听见
啊，
最后一句说的是啥来着？
没有，刚刚我旁边的同学问我要干嘛，然后我说了一句吃饭，然后说太大声了，
哦，
被全部人听见了。就是关于刚刚那个，就是那个排列组合的
啊，排列组合，
想你帮我捋一下高阶的逻辑。
高阶逻辑嘛，高阶的逻辑
就是以一个那个什么有梯度的一行一行一行一行，然后再踢回去的那个，
那就是这个样子对吧？
它什么东西？什么东西？
就是，就是输入4，输入3，输入2，输入1，然后 return 1，再 n 乘以什么什么什么。
对，那这个
接存那位，
这个一样呢。你看这个，你在 call 那个 permuted 124的时候，我第一个 round i 等于0 x 等于1，我得到了一个24，对不对？我把那个从中间删掉，得到了一个更小的数组24。我 call permuted of 24，
它就是再把24删掉，
对，
中的一个
对我进去
数删掉。
对对对，你看我进来了，我进来 v 等于24，对不对？我 i 等于0 x 等于2，我再把24中的一个数删掉，变成4，
对，变成4，
然后再去
把
permuted
2加在后面。
对，再把2加在后面。第二轮我把4删掉，把4加在后面，对不对？
对，之后然后再42的后面加上一个1，之后
对对对，
第二轮，
再返回
第二轮把24第二个删掉，再加回来。
对对对，
然后再变成1。如果更高阶的话呢，实际上就是先把4个删成3个，
对，
把3个删成2个，2个删成1个，然后每一个3个4个2个都进行一个一样的操作。
是的，是的，一模一样。
所以说递归是想不明白的，
就是你不要去想它后面怎么操作，你永远都需要一个假设。如果你要考虑3个的问题，你永远要假设2个的问题是对的，你不要去考虑它是怎么实现的。
就是我只要想清楚一种情况，
对，你只要想清楚一种情况，
然后
归纳法
跟它相似的所有情况我都假设它是对的，
对，
不能再去
归纳法嘛，
想它
对吧？你假设 n 小于等于 k 的都是正确的，那么你在计算 n 等于 k 加1的时候，
就是我
怎么去数学证
预
明？
习的时候我就发现，递归这个东西你很难把它的全过程给捋一遍。
特别是大了以后，
对，因为它
你要捋太多
重复的，太复杂。
这样子全部捋一遍，还不直接写个for循环出来？
对对对，是的，
这种就是我现在
有一些问题是不能用for循环处理的，
是，
就像这个汉诺塔的问题。汉诺塔的哪里？这个吧，是这个。
你就递归假设失败就
对，这个怎么思考？4个圆环，我假设你已经给我一个结果，能够给3个圆环是可以执行的。如果你告诉我一个方法，能够把3个圆环挪到另一个棍子上，你怎么去解决4个圆环的问题？非常简单，先把3个圆环放到中间，再把最后一个放到最右边，再把3个圆环放回去，搞定。你不要去思考3个圆环怎么过去的3个圆环怎么过去？我要思考2个圆环怎么过去，2个圆环怎么过去？我要思考1个圆环怎么过去。
其实就相当于我只要想一个最终的一步逻辑关系，剩下的交给计算机。
归纳法永远只考虑那一步归纳的那一步。
好，回去好好思考。
对的，就
那个递归就第一步是先想就最终那一步怎么做，
对，
然后第二步是想它那个最简单的情况。
我一般的想法是这样的哈，我一般是想法是先考虑一个更小的问题，比如说它是4个圆环的，我去考虑3个圆环的。假如说我已经有了3个圆环的答案，别人告诉我3个圆环该怎么挪，假设我已经有这个答案了，我该怎么去用这个答案，对不对？然后对于这个来说就是 OK， 别人告诉我3个圆环怎么从一个棍子挪到另一个棍子，我就把那3个圆环全部挪到中间那个棍子就好了嘛。
就是说，如果我原本只有3个，
对，
我就首先只有2个的情况我是肯定会的，
对，
我就把这个的逻辑写出来。
对，
之后呢，如果有3个，那3个呢，其实就是要在先把2个的逻辑执行一遍，
对，
然后最后再加一步。
对，是的。然后内部该怎么处理，就是这个问题。
但想问一下，就这道题的话，那怎么表示什么？这中间有没有杠啊？左边右边有没有杠什么这样？
你就可以 print， 比如说你每一步只要 print，比如说3根棍叫1、2、3，从1棍挪到2棍，从1棍挪到3棍，从2棍挪到3棍，从3棍挪到1棍，你只要表示出这个过程就可以了。
就没有一个就什么输入案例、输出案例这样子。
比如说你输入是4，他会告诉你，输入是1，他会告诉你从第1根棍子挪到第3根棍子 ，OK，
就1，然后一个
就是对箭头3，都可以，就是你可以自己表示。然后比如说是2个，你可以1到2、1到3、2到3，就搞定。对，
算法问题。这个下节课会讲。
对，下节课会讲，就我希望你们回去先思考一下，能不能把它想明白。能想明白，你们递归就 OK 了。
还有一个问题就是我发觉，就其实我们现在找的很多例题，它会涉及到一些超纲的东西，就比如那个 string，虽然我们现在还没学，但是其实例题中已经出现了很多，就包括那个自责运算那里，
对，
其实你没有办法用那个 pig 或者 get 是搞不到
的。其实也可以，你先把它全部读进来，一次性 get line，整行读进来，然后慢慢的看下一个是什么。
但是就是这些东西，如果我没有学过字符串，就都是看不懂的。
字符串怎么会看不懂呢？
哦，不是，就是那些东西嘛。
对，我在第1堂课、第2堂课我就提前讲 string， 讲了一点点。对，就是因为后面可能就语言的东西很难说哪个先教哪个后教，对不对？我完全不用 string， 那是不大可能的。对。
那还想问一下，怎么知道什么时候这个程序会更高效？
高效的话，你们明年有算法课，就会告诉你高不高效。但是你可以直接根据它的运行速度来嘛，
就是生成多少毫秒。
对，多少毫秒，几秒钟结束。
在哪里可以看到？我知道。
哦，那个的话，你装一个程序在 Linux 里是有的，你可以装一个程序，看到那个
Windows 不能。
Windows 我不知道怎么搞。
Visual Studio 2022的终端中会显示，
会显示几秒钟完成。
我刚开始用，不知道有没有。
但这样子的话，也就只有你写完程序才知道。
学完算法课你自己看一眼大概就知道了。比如说像刚刚那个 Fibonacci 那个，你看一眼就知道它肯定是比如说2的多少次方的那种概念，就它是一个指数型增长的速度，n 越大它是指数型增长。For loop 它就是一个线性的，对 ，n 是100，它可能就操作200次，那个的话可能就操作2的100次，
就其实 for loop 效率会比那个递归更高，但如果你 for loop 想不出来，就用一下递归。然后有些情况 for loop 又搞不了，又只能用递归。
其实绝大部分能够用 for loop， 但是就是思考起来会很复杂，有一些问题像汉用它那种思考起来很复杂，但用递归的话思考起来很简洁。对，就有时候你得要思考一下，到底你想要更简洁的完成，还是说要代码更高效一点。